Hello, college algebra students. So today we are going to talk about logarithmic functions, right? These logarithmic functions. So what are these logarithmic functions? So you write the logarithmic functions as something like this. Y is equal to log base b and x, right? So this is the base b. We always want this b to be positive, and this is your input. So what does that mean? This means the following. This is equivalent to saying, what is the power of the base, right? What is the power of the base? What is the power of the b that will give me x? That's what it means. So if I ask you the following question, what is the log for base 2? The question is, what is the power of 2? What is the power of 2 that will give me 4? You would say the answer is 2 squared equals 4, so therefore answer for this would be 2. So if I ask you the following question, what is the log 16 base 2? The question is, what is the power of 2 that will give me 16? You know that 2 to the 4 is 16, so the answer for this would be 4. If I ask you the following question, what is the log 3 base 9? Again, the question is, what is the power of the base, which is 9, that will give me 3? You would know that square root of 9, which is 9 to the 1/2, right? And so therefore the answer for that would be 1/2. So this is the basic understanding, the basic definition, the basic concept of the logarithmic function. So in general, you want your, here is the exponential function, and you get from there the inverse is actually the logarithmic function. So how do we graph them, right? The way that we graph them is, if you remember the graph of the exponential function, it looks like this: y is equal to b to the x, and for the same b, y is equal to ln logarithm of x is going to look like this. The reflection along the line y is equal to x would be the graph of that. By looking at the graph, the couple of things that we can observe. Number one, as you see here, the graph, this line y-axis, right, this line seems to be vertical asymptote, number one. Number two, this does not intersect, so therefore we can kind of, looks like the domain is somewhere here, right? The x values are somewhere here, and looks like the range seems to be the entire y-axis, right? So these are things that by just looking at the picture we can observe. So let me again summarize what we have, and then we will look at some important facts about these logarithmic functions. So the functions that we have, y is equal to log base b x. X is the input, right? X is always going to be positive. B is your base. B also going to be and must be positive. And y could be positive or negative, right? Y could be negative or positive and things along that line. We will do some examples. You will know what do I mean by that. So what is the domain, ladies and gentlemen? The domain, as I said, is going to be from 0 to infinity, 0 excluded. And the range is the entire real line, right? From negative infinity to infinity. And the graph passes through the points. Let's see, this point, if you remember, and that point is 1, 0. And the reflection of that point, on along the line y equal to x would be, that point is not 1, 0. That point is 0, 1. And the reflection along that line y is equal to x would be 1, 0, right? So the graph always going to pass through 1, 0. And the graph has a vertical asymptote. As I said, the y-axis is the vertical asymptote. At y-axis equation of the y-axis is x equal to 0. And the x-intercept is always 1. You cannot take a log of the number 0, log of a 0. That means log 0 base b is undefined. Also for this also applies for a negative, this also applies for negative numbers as well. All right, so these are some basic facts, some basic understanding of the logarithmic functions. So let's see how do we work with these logarithmic functions. Before I go any further, I want to quickly say one other point, so that will make our life a little bit easier later down the line. We know that when x is equal to 1, on the exponential function, when x is equal to 1, it's going to give you the b, correct? So the inverse, right, the opposite of that would be, when on the line y is equal to 1, you're going to have a b. In other words, when x is equal to b in the logarithmic function, y is going to be 1, something that I want you to. So what I'm trying to say is log b base b is always going to be 1, right? Something that I want you to know for right now, which will be very useful later. All right, let's take a look at these equations and try to write them in its equivalent exponential form. So again, if you recollect, the form is the following: y equals log bx is same as saying b, what is the power of the b? That's going to be x. And in other words, this is same as saying b to the y is equal to x, right? So b to the y is equal to x is same as saying y is equal to log x base b. Let's take a look at that. What do we mean by that in these problems? Let me copy this for us so that you can see it. So we're going to use this formula, right, for our purposes. Now what I have here is 3 is equal to log 7 log x base 7. So what does that mean? So here this would mean, here my y is 3, right? So it's going to be, and the base is 7. So this is same as saying so here's my, my b to the y is equal to x is y is equal to log bx. So let me pull it down here so you can see it better, right? You can see it better. All right. So if you see this, right? So b goes here. So 7 goes as the base, right? And the x is supposed to be on the other side, right? And the y is supposed to be on the power. So I have 7 cubed equals x. So that is the equivalent form here. So now here on the part B, and that is the answer for the part A. On the part B, what would that be? So again, if I paste it, so this is, I have this, right? So let me rewrite it for you so it's easier to see. Now this y is over on the other side, right? So again, this is b to the y is equal to x, right? So here my b is b does not change at all, b is b, and 25 is my x, so that is going to be 25 on the other side, and y is equal to 2, right? So the equivalent form is b squared is equal to 25, and here the equivalent form here would be just like we did earlier. This is going to be again y, right? So whenever you have log x base b equals y, means b to the y is equal to x. So therefore here I am going to have my base is 4 and the power is y equals the value, which is x, is equal to 26. So these are the equivalent forms of all of these, right? Now let's write down the example 2. Let's write down the other way. So what would be the other way? So now we have this. Again, let me copy paste it so you can see it better. B to the y equal to x, right? So that means what? That would mean in this case would be x equals, sorry, here in this case it will be y is equal to log b to the x, correct? So it's going to be, here is my y, that's 5, equals, here is my base and here is my x, right? So it's going to be log x base 2, right? If you take a look at the part B, my base is b, so it's going to be x equals, right? The power is going to be x equals log 27 base b. If you take a look at the third one, again, so if I apply this, so now I have b to the y is equal to x, and so therefore that's going to give you log x base b is equal to y, right? So therefore here I would have log base is e and the x is 33 is equal to y, which would be y. And that's how we would write these things, right? All right, so now let's try to evaluate these ones based on the understanding of how does the logarithms work. So now I have log all right, now I have log 9 base 3 is equal to y. So that means, as I said earlier, whenever someone asks a question, y is equal to log bx, that means the question is what is the power of the b what is the power of the b that will give me so let's see, so this means what, b to the y is equal to x, right? So what is the power of the b that will give me x, right? So in this case, what is the power of 3 that will give me 9? The power of 3 that will give me 9 is, we know that 3 squared equals 9. So therefore the answer for this would be 9. Same thing in here. What is the power of 36? That will give me 6. You know that square root of 36 equals 6, which means the power of 36 is 1/2. So answer for this would be 1/2. And here is what is the power of 5? That will give me 125. You know that 125 can be 1 over 125 can be written as 1 over 5 cubed, which then can be simplified as 5 to the negative third, right? So the 5 to the negative third is 1 over 125. So the power of the 5 that will give me 1 over 125 is negative 3. So therefore the answer for this would be negative 3. And that's how we would solve these kind of logarithmic problems. Simple problems, but let's take a look at how do we solve a little bit more complicated, a little bit more fun ones later. All right, so let's to move forward, we are going to learn two important logarithmic functions. These are common logarithmic functions. The number one is the common log base 10, and the other one is what we call natural log, which we will use them very much, which is log base e. E is the number 2.7 something that we talked about in the previous section, right? This is called the common log, and the usual traditional way of writing, it's customary to write log base 10x as simply log x. So if you don't see a base, that means by default the base is 10, and it's customary to write log x base e as ln of x. So if you see the symbol ln, that means the base is e, right? These are the customary ways of doing it. So here someone asks you what is the log 100. There is no base here, that means this is same as saying log 100 base 10. The question is what is the power of the 10? That will give me 100. You know the answer is 10 squared is 100, so therefore it should be 2. What does it mean to be ln of 5? That is same as saying log 5 base e. This is not as simple as this. So the question here is what is the power of e? That's going to give me 5. That is not as simple as the previous one. We will see how do we do that using calculators later. So some of the basic properties of this logarithm, right? Log b to the 1 is always 0. So whenever your input log x base b, as I said, x is your input, right? Whenever your input is 1, no matter, it doesn't matter, I don't care what the base is, as long as the base is positive. Otherwise it doesn't make any sense. As long as the base is positive, our answer is always going to be 0. That's same as saying the line passes through 1 comma 0. Log base b, if the base is same as the variable, it's always going to be 1. That is same as saying b to the b is always 1. Log base b b to the y, right? Again, what is the power of the y? What is the power of the b? That's going to give me what is the what is the power of the b that's going to give me b to the y? It's going to be always y. So therefore that's what we have. And as I said, exponential and logarithmic functions of inverses of each other. So therefore b log bx, right? B log bx is always going to be x. See, so these are some basic properties for any base b. This is for any base b as long as b is positive. All right, so let's take a look at some of the properties of the common log. So log 1 is always 0, log 10 is always 10, log 10 to the y is always y, 10 log x is equals x. Similarly, if you take a look at the natural log form, ln of 1 is always 0, ln of e is always 1, ln of e to the y is always y, e to the ln of x is always x. Also, I should tell you, ln of e to the x is also x, and e to the ln of x is also x. Something that you should know, right? Something we'll be using it a lot. Similarly here, 10 to the log x is x. Also, log 10 to the x is also x, right? So we looked at it before. So these two together, because the reason is exponential function and the logarithmic functions have inverses of each other. So when you could, this is basically composing exponential and logarithmic functions. When you do that, that is what you're going to get. All right, let's use these properties to evaluate the following. Since let's take a look at this one, log 9 base 9. Since the base and the input are same, in other words, they have the same value, so there's always going to be 1. Since the input is 1, the answer is always going to be 0. This is log 7 to the 8 base 7, the answer is going to be 8. And here 3 base is same as the power, so this is going to be inverse property, the answer is 17. And this is 10 log 6, log 6 means log base 10, so the power and the base is the same, so the answer for this would be 6. ln of e is always 1, and ln of e to the 8.2, as I said earlier, ln of e to the x is x, right? So therefore this is my kind of x right there, so the answer is going to be that value right there. And here, what is the log of 6, square root of 6 base 6, and that would be, you know that I can rewrite this as log 6 to the 1/2 base 6, which is 1/2, right? So that's how we would do all these, that's how we would evaluate all these logarithms. All right, so let's move on to how do we find the domain. All right, let's take a look at how do we find the domain. As I said earlier, ladies and gentlemen, what do we know is that if you have the function y is equal to log x base b, the domain is 0 to infinity. In other words, the input should be always positive. It cannot be even 0. It always have to be positive, right? It cannot be 0, and that is the idea that we are going to use in this case. So remember this, and that's what we're going to use, right? This x input must be always greater than 0. So for this particular function right here, we are looking at the domain, and the input here is not x, but rather it is x minus 6. So whatever the input is, I want that to be positive, otherwise it does not make any sense. So therefore, excuse me, therefore, I want my input, in this case, which is x minus 6, to be positive, and that tells me x must be greater than 6. So therefore, the domain in this particular case would be all the numbers starting with 0 and going all the way up to infinity, right? And that is the same idea that we're going to use to solve the second problem as well. And again, I want the input to be positive. My input here is 5 minus x, and I want that to be positive. That tells me that 5 must be greater than x. In other words, this is same as saying x must be less than 5, and so therefore the domain for this would be negative infinity all the way up to 5. So that is the domain for this. So some of you don't get confused. Although we said for the logarithmic function, domain cannot have negative numbers, these are not going to give you negative numbers. When I plug in these numbers into the log, these are all going to give me positive numbers. So for example, if I say 4, if I plug in 4, 5 minus 4 is 5 minus 4 is 1, so that's okay. If I plug in negative 5, 5 minus 5 would be 10, so that is still positive, right? So whatever the inside, when I plug in numbers from this domain, when I take numbers from this domain and plugging in into my logarithmic function, and the inside, the input is always going to be positive, so therefore this is well defined. All right, let's take a look at this problem. Again, as I said earlier, I want the input to be positive, right? So here I want my x squared minus x minus 2 to be positive. We did a problem like this in the previous chapter. So the way that we do is we first set it equal to 0. When I set this equal to 0, and then I want to find the values that will x values that will make this 0. In this case, that would be x minus 2 times the x plus 1, and if I factor them out, and in this case the values that will make my the expression 0 would be x equals 0 and negative 1. And if you remember, we divide the entire real line into number of parts based on these values. This is negative 1 and this is positive 2, and then we pull out a test number in this domain, test number in this domain, test number in this domain, in this part, in these intervals, right? So we have 1 here, we have 1 interval here, we have 1 interval here, and we have another interval there, and we have another interval here. And if I plug in negative 2, if I plug in negative 2 and 0 and 3, right? If you plug in negative 2, 0 and 3, that's going to give me where it's going to be negative or positive. Let me plug in negative 2. When I plug in negative 2, so this would be when I plug in negative 2, this would be, let's take a look, negative 2 the whole squared minus 2, which is positive 4, positive 2, minus 2. All right, that is going to give me positive 4, so that is positive, so this is okay, that interval is good. Let me plug in 0. When I plug in 0, this is when we plug in x equals negative 2. When I plug in x equals 0, I will have 0 squared minus 0 minus 2, which is negative 2. So that's not the interval that I'm interested in. Let's take a look at the next one. Let me plug in 3. When I plug in x equals 3, which would give me 3 squared minus 3 minus 2, which is 9 minus 3 minus 2. Again, I don't care about the number, all I care about is the sign, so that's going to be positive. So here I am going to have positive. So the intervals in which this expression is positive is going to be negative infinity to negative 1 union 2 to infinity, and that will be my domain. There is another easier way to do. Probably when I have some other time, I'll let you know. There's another easier way to do for whenever we deal with them, by the way. All right, so let's take a look at the next one. So here we have to find the domain of this particular function, which is a rational function. The good news is both are linear factors, right? So what I have here is I want my x plus 1 over x minus 5 to be positive. So we are going to use a kind of a different idea in here to do that. When do you have, whenever you have some rational numbers, right, when would that be positive? So if you have a number p over q, when would that be positive? If both p is positive and q is positive, right, the outcome is going to be positive. If both p is negative right? If p is negative and q is negative, right, still I'm going to have a positive, right? So that is the idea that we are going to do, right? So what do I mean by that? So for this to be positive, if I have the numerator, if that happens to be positive, and the denominator, if that happens to be positive, that's going to give me positive for the entire expression. Similarly, if the denominator is negative, if the numerator is negative and the denominator is negative, that is going to also give me positive, right? So when would that happen? So let's take a look. When would that happen? When we say the first case, I want x plus 1 to be positive, that means my x has to be greater than -1. For x minus 5 to be positive, I want x to be greater than 5. So what is the common interval that satisfies both of these conditions? And that would be, so if you take a look, here is my entire real line, here is my 0, here is my -1, here is my 5. In this particular section, x plus 1 is positive. In this particular section, x minus 5 is positive, but I want the common one, so here is my common one. So therefore, this gives me the numerator, the entire numerator and the denominator positive. That will happen in a case when the x values are between 5 and infinity. So this is the case when the numerator is positive and the denominator is positive. So I'm going to write it, I'm going to put it over here. All right. Now let's take a look at the second case. I want the x plus 1 to be negative. I also want the x minus 5 to be negative. So to do that, this tells me x must be less than -1 and x must be less than 5. Let's take a look at the common interval in which both of these conditions would be satisfied. So if I graph them, so here is my entire real line. I just say here is my 0, here is my 5, and here is my -1. I want both of them to be negative. I want both of them to be negative, right? I want both of them to be less than. So in this interval, x minus 5 is negative. In this interval, x plus 1 is negative. So in this, together, both are negative. Since both are negative, the ratio between them is going to be positive. So here what I am going to have, the interval in this case would be -infinity all the way up to -1. So here we have another interval where my rational function is positive. So we have to combine these two together. So therefore the domain, so let me use a different color. The domain would be, domain in this case would be 5 comma infinity union -infinity comma -1. This 5 comma infinity comes over here from there, and then -infinity comma -1 comes from there, right? And that's how we would find the domain of this. And by the way, that is a similar idea you can also use for this particular one as well, right? For example, you want the product to be positive, right? You want the product to be positive. So therefore what you can do, now you have two factors, two ways this can be positive. One is both of them positive or both of them negative, and then you can work with that and find the appropriate interval for this also. So if you want to, as a homework, try this. Find the intervals in which this is positive and this is positive, and this is negative and this is negative. The top one is going to give you 2 to infinity, and the bottom one is going to give you -infinity to -1, and the union of that would be the answer. And it's very similar to what we did in the other case. So something that you can think about it. All right. So let's try to graph these functions, and we will call it a day. So if now I have the graph log x minus 6, right? How do we graph the log x minus 6? So this is the base 3. One of the easier way to do that would be first we find the graph log x base 3, and then we can see this is x minus 6 means it's a transformation 6 unit to the right. So we can do that. So log base 3x, how is it going to look like? Let me first graph 3 to the x. 3 to the x would be, here is 0, 1, and at 1 it is going to be 3, and at 2 it's going to be 9. So here is my graph y is equal to 3 to the x, right? So y is equal to 3 to the x. Now I'm going to reflect this along this particular line right there. Y is equal to x. The reflection is going to look something like this: 9, 3, 1. The reflection is going to look something like that. I'm not doing a good job there. That's how it's going to look like, right? Now we have to move this 6 units to the right. If I do that, then here the graph would be 1. So let me try to graph it properly. So if I move this 6 units, 1, 2, 3, 4, 5, 6 units, right? The graph is going to look like something like that. Like that. There should not be any curves in here. There should not be any things like that. So it's going to look like this. All right, that's how it's going to look like. Now we have the next one, which is this right here, 3 plus log x. So what we can do, log x means, you know that this means this is same as saying 3 plus log x base 10, right? So we can graph the way we can graph them is first we graph the ln log of x, log base 10x, and then this means adding 3 units. That means basically moving up by 3 units by the transformation. So graphing that would be, let's try to graph the function 10 to the x first and then reflect it, or we can directly graph in this case 10 to the x. So let me graph it. 10 to the x, it's going to be 1, and at 1 it's going to be 10, so it's going to be very steep. It's going to be very steep. And if I do the reflection is going to be at 10, it's going to be 1, it's going to be 0, it's going to be like that. And then we're supposed to move this by 3 units. If I do that, it's going to be 1, it's going to be 1, 2, 3 units, so it's going to be looking like that. So the graph would be this particular one right there. It may not be accurate, but you get the idea. They should not intersect, so I need to put it properly there. Something like that. This is the graph, which is 3 plus log x, right? And that's how we graph these particular functions. I will stop it right here. We will look at when we come back. Go home and do this, right? Try to finish this part. When we come back, we will try to look at some properties of logarithms, and then how do we use the logarithms properties to solve some cool expressions that involves logarithms. All right, ladies and gentlemen, I will see you all later. Have a great day.